Okay, so let us do an example for the compressor isentropic efficiency. Okay, so in this problem, what do we have? We have refrigerant 22 enters a compressor at 3.5 bar and a temperature of -5 degrees Celsius and leaves at 14 bars and a temperature of 75 degrees Celsius. Determine the compressor isentropic efficiency. Okay, so if we first do a sketch for the compressor, so let's say over here we have refrigerant 22, and we know that initially will be at 3.5 bars and a temperature of -5 degrees Celsius, and will be leaving at P2 equal 14 bars and a temperature of 75 degrees Celsius. Okay, and we know that a compressor, in order to work, requires power or work. Okay, so I think the first thing to do over here is actually to find out what is the state. So we'll have to do here a figure. Okay, personally the one I like to do is the V or S, and here we can put the temperature. So let's say we have something like this, and I know it will be V, we can use line of constant pressure, but first let me just look at the state. So let's see, let's say state 1, what do we know? P1 equal to 3.5 bars and T1 equal to -5 degrees Celsius. Okay, so if we go to table A8 at P equal 3.5 bars, you find that the saturation temperature is 3.5 bars is -10.39. -10.39. However, the temperature here is -5. So what does that mean? That this one is hotter than this one. Okay? So we're going through a line of constant pressure. Let's say this way. I just do this part over here. So let's say it will be P1 equals 3.5. The temperature over here, the saturation temperature, is -10.39. Okay, since we're at -5, it should be somewhere higher. So let's say that we are somewhere over here. All right, let me go over here. Do this. So it will be our state 1. Now, so basically we know is superheated. Okay, and if you want, since we are here, maybe we can look at what happens for the other one. So state 2, P2 equal to 14 bars, T2 equal to 75 degrees Celsius, and from table A8 at P equal 14 bars, what do we get? T saturation, so this is lower than T1, superheated. T saturation is, so I know you cannot see, but at 14 bars, T saturation is 36.29. Let me zoom out now. .29. Okay, Celsius. So what do we know? This is lower than T2, which is 75. So this also will be superheated. Okay, so we'll go through another line over here. P2 equal to 14. Alright, so now what happens? We know that in a compressor, in a compressor that is not ideal, is going to use more power, is going to waste some power. So we know that the entropy should also increase. So we know that state 2 is going to be here, somewhere of increasing entropy. So this could be the actual process. But what happens if we have something ideal? We know that S1 will be equal to S2. So in this case, we'll go through a straight line over here. And this should be 2S. Okay? So personally, I like to define, in this case, what is efficiency. So remember, the efficiency is always lower than 1. So in other words, what do we need to have? We need to have the highest value dividing. So what is higher? H2S minus H1 or H2 minus H1? So obviously it's going to be H2 minus H1. So at the top will be H2S minus H1. So this will be the expression for the efficiency. So basically, in order to find the value for the compressor efficiency, we need to determine H1, H2, and H2S. And we need to go to which table? The superheated tables. Okay? So let's go first and find what would be H1. So for H1, we go to table A9. Okay? And what do we know? We need to know two things. So the first thing we know about the first one is what? Is that the pressure is 3.5 bars and the temperature is minus 5 degrees Celsius. So if we go to table A9, let me zoom in a little bit. For 3.5, it's not that clear. So 3.5 and a temperature of minus 5. What is H is 249.75. We have that H1 equal 249.75. Okay, and also we can see that S1 will be equal to 0.9572. S1 will be equal to 0.9572. Why do we need the S? Is because in order to find H2S, we're going to use the condition that the process is isentropic, so S1 should be equal to S2. Okay. Next, we can do the same thing for state 2. So let's say from table A9 at P2 equal to 14 and T2 equal to 75. degrees Celsius. So in this case, the only thing we need is H2. So at 14, that's not the table that we need. There we go. So at 14, we don't have 75, but we have 70, where H is 290.01 and 80, 298.34. So basically, we can just add these two and divide by 2, and that should give us the value of the enthalpy at 75. So if I copy that, what do we get at 14? We get that this would be equal to 290.01 plus 298.34 divided by 2. And if we do the calculation, we get a value of 294.175. Okay? So far, we have H1 and H2. We need to find H2S. So in order to find H2S, we're going to use the condition that, so we're also going to need table 8-9, but we're going to use the condition that at S2 equal S1 equal to 0.9572, and the other condition is what? We are along a line of the constant pressure, so that means that at P2 equal to 14 bars. So basically what I need to do is go to the tables for the 14 bars, which is over here, and find and interpolate for the S2 we found. So we have 0.9572, so we see that will be between these two values over here. So for these two values over here, so let's say, so that will be between 60 and 70. Okay, so let me copy those values. Let's see if you can see them. It's going to be difficult. So you go to the table A9 for the pressure 14, and actually if you look at the temperature of 60, we'll have that SA, let me call this one, will be equal to 0.9452. So that's at 60 degrees when T equals 60. And let me call this one S sub B, will be 0.9703, and this is at T equal to 70 degrees. Okay, so now we need to interpolate because we know the value of S. So let's see. So we're also going to need the H values then, because that's what we are looking for. So the same thing, we're going to have HA is equal to 281.53, H sub B 290.01. So if we do the interpolation, remember that for the interpolation, you put on the y-axis what you're looking for, and you put over here what you know. So in this case will be S. So we'll be interpolating between 2 points. This is A, this is B. So that, let's see, what will be the interpolation equal to? See if Let me zoom out a little bit. Okay, so we'll have then that H to S will be equal to what? HA plus H sub B minus H sub A divided by S sub B minus S sub A times what? S2 minus S sub A. Okay, so if we put the values, we're going to get 281.53 plus 290.01 minus 281.53 divided by 0.9703 minus 0.9452, and that difference in distance is equal to S2, which is 0.9572 minus F sub A, that is 0.9452. So if you plug the numbers, we're going to get that H to S will be equal to 285.58. So this will be the third value that we need. Okay, so remember that the efficiency, if I go and look for the first page, the efficiency of the compressor is equal by this expression. So that we can say that finally the efficiency of the compressor, which is given by H to S minus H1 divided by H2 minus H1, will be equal to what? Will be equal to 284. Sorry, no. 285.58 minus H1, which is equal to, I need to find that other page, 249.75 divided by 294.175 minus 249.75, and this gives you an efficiency of 0.806, which is approximately 81%. Okay, so this will be the end of this one. Thank you for your attention.